Hello everyone. In this video, I'm going to go over the Math-108 homework on probability with not and or. So for the first question, I have a bag containing 12 marbles. 5 are red, 3 are green, and 4 are blue. And we're going to reach in and take out 3 marbles in order without replacement. What is the probability of getting, and then we have some different events. So for the first event, we want the probability of getting all red marbles, so 3 red marbles. So for this probability, I'm just going to do it the standard way. So on the top, I'm going to do the number of ways to get 3 red marbles. And on the bottom, I'm going to do the number of ways to get any 3 marbles. So just any outcome for the experiment. And the experiment is taking out these 3 marbles. Okay, so how many ways are there to get 3 red marbles? Well, there's 5 red marbles, so we have 5 choices for our first marble, and then we'll have 4 for the next one, and then 3 for the third one. And we are able to use the fundamental principle of counting and just multiply the number of options together for each marble because we're considering these choices to happen in order, which means that the order that we get each marble in makes a different outcome. I guess we're assuming like we have some way of distinguishing these red marbles. They could be distinguished from each other. All right, so on the bottom, the number of ways to get any 3 marbles is 12, 11, 10. Okay, so it's pretty much going to go the same way for the next 2 questions. In fact, it's so similar that I'm going to be really efficient. I'm saying efficient instead of lazy. And I'll just paste this text here and just put the word different colors. Okay, so once again, the number of ways to get 3 green marbles. We have 3 in the bag, so 3 choices for the first one, and then 2 choices for the second one, and 1 for the last one. And then the same denominator as before. It's the same experiment, so we got the same denominator. And then for question 3, again, it's the same experiment, so this denominator is the same. And on top, for 3 blue marbles, I have 4 to choose from. So I have 4 choices for the first one, and then 3, and then 2. Okay, so that was the first 3 questions. Not too bad, hopefully. The 4th and 5th questions are a little more challenging. So all the same color. So all the same color, you might think we could just do something like this, number of ways to get 3 of the same color. And then on the bottom, number of ways to get any 3 marbles. Well, this is a valid way to approach it. But depending on what you do next, you might do something that won't work. So you might say, okay, well, let me just start off with any marble. And then after that, I'll try to match whatever color I got on the first marble. I'll try to choose another of the same color. But the problem now is that you don't know which color you got, right? Because there's a different number of each kind. If you picked red first, then there will be 4 left. If you picked green first, there will be 2 left. And if you picked blue first, then there will be 3 left. So you don't know what to put for the second number. So you can't do it this way. You have to take a different approach. So the approach we want to take is to interpret this all the same color event as actually 3 different events, and then we're going to put ors between them. So all the same color really means all red or all green or all blue. Okay? And now we didn't learn any formula for the probability of 3 events unless those events are mutually exclusive. So we better hope these are mutually exclusive, because if they're not, then you got some weird overlapping stuff you have to deal with. Okay, so are these actually mutually exclusive events? Is it possible for me to get all red and all green? Well, not on the same draw of 3 marbles. We're still just doing this experiment where we take out 3 marbles. You can't get all red and all green on the same 3 marbles. So these are mutually exclusive events. These are mutually exclusive events. Okay, and that's really good because since these are mutually exclusive events, that means that we can calculate the probability of at least one of them happening by just adding them together. So we're just going to add together the probability of 3 red plus the probability of 3 green plus the probability of 3 blue. And we don't need to worry about subtracting any overlaps because there won't be any overlaps. There's no way for both events or all 3 events to happen at the same time. So that means we can just literally just copy these answers from 1 through 3 down here. And that's the answer. Now for number 5, we want to know the probability that we get 3 marbles that are not all the same color. So it doesn't mean 3 different colors, it just means not all the same color. So 2 of them could be the same color as long as they're not all the same color. So this is a bit tricky to do, and again, you can't approach it by just doing this kind of look at your options on the first, second, and third. And the reason you can't is because let's say you try to do it this way. How many options do you have for your first marble? Well, there's nothing to match or not match yet, so just any marble is okay. Then you go to your second marble and you're thinking, well, okay, I just have to make sure these marbles are not all the same color. So actually any marble would be okay here, as long as I don't match on the third one. But if you do it this way, then when you get to the third one here, at this point, some of the ways that you could have chosen the first 2 marbles would have been different colors, so you would have 10 options left. But some of those ways of choosing the first 2 would have been the same color, and if they were the same color, then you would have to pick a different color. Well, we don't even have the same number from each color, so you definitely don't know what number to put at this point. So you cannot approach it like this. It just won't work. So what you've got to do is use that 1 minus formula instead. So the probability that an event does not happen is 1 minus the probability that it does happen. So we're going to do 1 minus the probability that those 3 marbles are all the same color. And we know how to do that because we just did it. It's this number up here. It's long and complicated, but it's just a number. So all we have to do is just 1 minus, and then I'm going to put parentheses around this whole thing here. This long, big, beautiful number, and make sure that's all being subtracted and not just the first term by putting it in parentheses, and that is the answer. So not too bad if you understand the concept of taking the opposite of an event. Okay, so in spring 2026, there are 2,089 students enrolled at SU, and I've categorized their majors here into the 3 schools. And we also have some undeclared students, and then we have the 4 years. And so all the different subgroups are represented in this table. We're going to choose a random group of 10 students for a focus group. There are no special roles in the group, so that means the order of selection does not matter. So if we're choosing without order, then we're going to be using that choose notation where you have one number on top and another number on the bottom, but it's not a fraction. It's just a notation that stands for a big long formula. Okay, what is the probability that all 10 students chosen are seniors or all 10 are business majors? So now I need to use my OR formula for probability, and let's just think about this for a second. Are these events mutually exclusive, or could they happen at the same time? Is it possible for me to choose 10 students that are all seniors and are all business majors? Well, yeah, there's 148 seniors that are majoring in business, so yeah, that could definitely happen. So I do need to not just add together these probabilities, but I need to also subtract the overlap. Okay, so I want the probability that I get all seniors plus the probability that I get all business minus the probability that I get all business seniors. So both groups, both business and seniors in the same 10 students. Okay, so I'm doing fraction plus a fraction minus a fraction. So for all of these, the experiment is choosing a random group of 10 students. So the denominator here is going to be number of ways to choose any 10 students for all of these. Any 10 students. So I'm just going to copy that into these other fractions here. In fact, you could combine this into just one big fraction with the plus and the minus part on the top. That's also fine. So on the top of the first one, I want to have number of ways to choose 10 seniors. Next, number of ways to choose 10 business majors. And then lastly, number of ways to choose, so students that are both business and seniors. Can't spell choose. And let's say business seniors. Really serious seniors. They got business. Oh, sorry. Sometimes you get bored making these videos, and you just want to make some dumb jokes. All right. So you might say that this part that I've done, like everything here, I think I see a lot of times students are trying to skip over this part because they think, oh, it's just a bunch of words, like it doesn't matter. But this is the part where you're actually like setting down your thinking on paper and so that you can look at it and see if it makes sense or not. So if you don't do this part, not only are you more likely to make mistakes, but you won't be able to review your work and follow the steps along and see what you were thinking when you were doing it. So that just makes everything harder. I strongly recommend that you actually do this step where you put down these little quasi-English formula things like I'm doing right here. I'm not just doing it for like to help you understand. I'm doing it because this is really the best way to do it. Okay, so now let's actually fill in some numbers here, or actually some notation. So the number of ways to choose 10 seniors, we're going to use that choose notation because we want to do it without order. It doesn't matter what order they join the focus group in, they're just going to be on the focus group. So seniors, how many do I have? I have 478 seniors, and I'm going to choose 10 of them. So this notation here stands for the number of ways to have 478 items and then choose 10 of them in no particular order. It actually is short for a much longer formula. And then on the bottom, just the number of ways to choose any 10 students. So I'll start from the whole group of SU students, 2089, and choose 10. All right, and then the next two fractions are going to be similar to this. So the denominator will be the same, for each of them. So let me just copy that. And then on the top here, I'm trying to do the number of ways to choose 10 business majors. So business majors, I have 653 of them. So this will be 653, choose 10. And then for the last one here, I want the number of ways to choose 10 business seniors. So students that are in both groups, business and seniors. So that is this group right here, the 148 seniors that major in business. So 148, choose 10. Okay. And then now you have a formula that you could actually go to Google and plug in and get the actual percentage if you wanted to. Okay, let's try the next one. Not all 10 students chosen are business majors. So be careful with how you interpret this. It doesn't mean that they're all not business majors. It simply means they're not all business majors. So 9 of them could be business majors as long as the 10th one is not. So there's a lot of different ways this could happen. They could be all not business majors, or you could have 1 or 2 business majors, or any number of business majors, as long as it's not all 10. Okay? So the words not all and all not mean something different. Right. So how are we going to do this then if we don't know how many business majors we're going to need to pick? Well, that makes it really hard to approach it in a direct way, but we can approach it in an indirect way. Because this event starts with the word not, we can just do the not formula, 1 minus the probability of the event that comes after the word not. So probability that all 10 students are business majors. So all 10 business. All right, this is much easier to do. We already know how to do it because we actually did it up here, right? Oh no, it was this one, right? That was probability of all business. Okay, so I'm just going to do 1 minus number of ways to choose 10 business majors over number of ways to choose any 10 students. And here is what I get. Oh, parentheses went away. So on the top, there were 653 business students, and I want to choose 10 of them. And then on the bottom, any 10 students, there's 2,089 of them, and I want to choose 10. All right. Number 8, all 10 students chosen are from the same year. Okay, so you might think you could approach this kind of like a cards question, like first pick the suit and then choose the 10 students from the suit. And it would work for cards, but the problem is that we have a different number of students in each year. So they're not like suits where you have 13 in each group. We have a different number in each group. So this is much more similar to this question up here where we had all 3 marbles being the same color. It's very similar to that. We need to break this into 4 events. So this means all freshmen, or all sophomores, or all juniors, or all seniors. Okay? And I hope to goodness that these are mutually exclusive events, because if they're not, when you have more than 2 events, you have to do much more complicated accounting for all of the overlaps that you might over or undercount. So are these mutually exclusive events? Could we possibly choose 10 students and then find out that they are all freshmen and all sophomores? No. Every student is only 1 year, so only one of these 4 things could possibly happen. None of them can happen at the same time. Okay, so what we want to do then is probability of all same year. We're going to get that by doing probability of all freshmen plus probability of all sophomores plus probability of all juniors plus probability of all seniors. I'm just doing some little abbreviations here so that I've written down enough that I kind of understand my own work. All right, so this is going to be fraction plus fraction plus fraction plus fraction. And we don't have to worry about subtracting any overlaps because there are no overlaps. That's what it means to be mutually exclusive. Okay, so on the top, I want to have number of ways to get 10 freshmen. On the bottom, number of ways to get any 10 students. And then I'm basically going to do the same thing across all of these. So the denominators are all like that. And then the tops are going to be number of ways to get 10 sophomores, number of ways to get 10 juniors, and then number of ways to get 10 seniors. Okay. Now let's put in the actual choose notation. Oop, one went wrong. Okay, so on the bottom of all of these, it's going to be the same denominator we've been using, 2,089 choose 10. It's just the number of different outcomes for the committee in general. And then on the top, we're going to be choosing 10 each time, but we're choosing from a different number. So first we'll choose from the freshmen, and then the sophomores, and then the juniors, and then the seniors. So we're going to use these 4 numbers here, 437, and then 562, and then 612, and 478. All right, and whatever that adds up to, that is the answer. And then number 9, not all 10 students chosen are from the same year. Okay, so you notice this is the same as number 8, but with the word not in front of it. That means we can use our not formula. So probability not all same year is going to be 1 minus the probability that they are all the same year. And we just calculated what that was. So all we have to do is just copy it down here and subtract it from 1. And we get this big, beautiful number here. All right. Number 10, all 10 students chosen are undeclared, or all 10 students chosen are freshmen. So this is very similar to the first one that we did up here, seniors or business. We're just using freshmen and undeclareds instead. So we're going to do probability of all undeclared or all freshmen. I'll just abbreviate like that. It's going to be probability that all are undeclared plus probability all are freshmen minus probability of all. And now we want to have the students that are both, so undeclared freshmen. All right. And I think maybe I'll skip over like this part of it and just go to the numbers or to the choose notation. So fraction plus fraction minus fraction. So on the bottom, we're going to keep having the same denominator we've been using the whole time. The number of ways to perform the experiment of choosing any 10 students. And on the top, we're still choosing 10 for each of these. Boop, boop. But first, we want to look at the undeclared students. So that's going to be, there are 79 in total. So 79. And then all freshmen. So that's 437. And then undeclared freshmen is this number right here, 67 of them. And that's it. Okay, for the last two questions, these are a little different. So you remember that mystery box that you might have seen in class where I have 5 marbles. And let's say you don't know what's in the mystery box, but I'm just going to go ahead and tell you that the box contains 2 white marbles and 3 black marbles. Okay, so that's the right answer, but you kind of imagine that you don't know this yet. So you are going to try to figure out how many black and white marbles make up that 5 marbles by doing these observations. So you can shake the box. Sounds like this. And then you're going to look in the corner at a really small little window, and you can just look at 1 marble at a time that will fall down into that window. Okay, so you can only see 1 marble at a time, and you cannot remove any marbles, so you're drawing with replacement. So your plan to figure out how many marbles are black and how many are white is to do 10 observations. So you're going to shake up the box 10 times and look at 1 marble in the little window. So there's 11 possible outcomes that could happen. So out of those 10 times, you could see white none, like 0 times, and see black 10 times. That's possible. I mean, there are white marbles in there, but it's possible that you just randomly don't see those ones. Or you could see white 1 time and black 9 times, white 2 times, black 8 times, and just so on and so forth, like this, all the way down to the end. You could see white 10 times and black 0 times. So I have gone ahead and calculated these probabilities for you. And this is not a problem that's going to go away. We're going to keep talking about this concept because it's very relevant to sampling, statistical sampling. So I went ahead and calculated these probabilities for you. The probability of each of these events, well, I'm calling them outcomes, but they're more like events, I guess. Right, so I did these calculations. And then let's say that you've already made up your mind what outcome would make you guess what proportion of black and white marbles. So basically, like, you've already decided, okay, if I see black 10 times in that little window, then I'm just going to guess that there's all black marbles in there. That's a pretty good guess, right? That makes sense. You didn't see any white ones, so there must not be any white ones. And then if you see white 1 time, well, you know there's at least 1 white one in there, right? So then, but there's not very many white ones because you only saw it 1 time out of 10. So then you would guess 1 white and 4 blacks. And then if it's 2 and 8, then that's like the same proportions as 1 white and 4 black. So that guess should make sense, hopefully. Yeah, so I just went through here and like put what guesses I think would make sense in each of these situations. And the only one where you kind of can't like totally decide well is when you see half and half, because you know there's 5 marbles. If you see exactly half white and half black, it's like, how do you decide between 2 white, 3 black, or 3 white, 2 black? So I said what I'll do is I'll flip a coin. Well, theoretically, you are doing this. I guess it's really my idea. So you're going to flip a coin to decide between those 2 guesses in this case. All right. So now what are the actual questions? What is the probability that you guess right? So I calculated these probabilities here under the assumption that the box really does contain 2 white marbles and 3 black marbles. So I had to have that information to calculate these probabilities. So as you see, the most likely thing that would happen is actually that it comes out the same proportions. 2 out of 5 are white, which is the same as 4 out of 10. And 3 out of 5 are black, which is the same proportion as 6 out of 10. So this is the most likely outcome. But these other outcomes aren't too unlikely. I mean, this is almost as likely that you would be like 1 off from the most likely one. And they kind of taper down as you get further away. Like, all black is really unlikely. All white is even more unlikely. Right, so what is the probability that you guess correctly? 2 white, 3 black. Okay, well, what are the different ways that that could happen? So guessing 2 white and 3 black could happen if I see white 3 times and black 3 times. And black, or sorry, 7 times. Or it could also happen by seeing white 4 times and black 6 times. And there's another way that it could happen. I could also guess 2 white and 3 black if I see 5 and 5 in the window, and then I flip that coin and it does land on whichever side I designate, heads or tails, whichever one I designate to be for guessing 2 white and 3 black. So this one's a little trickier to figure out, but that's the third way this could happen. Or it could happen if I see white 5 times and black 5 times, and I flip the coin to guess 2 white, 3 black. Okay, so there's 3 distinct ways that I could guess correctly. And now any of these 3 ways will give me the right guess. So what I want to do is basically just add them up. And I don't need to worry about subtracting any overlaps because these are all mutually exclusive outcomes here. If I saw 4 white marbles and 6 black in the little window, then I didn't do any of these other things, right? Because I'm only shaking up the box 10 times. Okay, so these are mutually exclusive outcomes. So we can just add up their probabilities. Let me organize this a little more, maybe with some bullet points. Let's do like this. So if I see white 3 times and black 7 times, or white 4 times and black 6 times, or white 5 times and black 5 times, and I flip the coin to guess 2 white, 3 black. Okay, so I need the probability of these 3 things. So if I see one of these, so probability of white 3 times and black 7 times is this number here, 21.50%. So I'll just put that here. White 4 times and black 6 times is this one, 25.08%. And then what's the probability of this? So that I know there's a 20.07% of seeing half and half, 5 white and 5 black. But what's the probability that that happens and then I flip a coin and I land on the 2 white, 3 black side, whichever I said that was, heads or tails? So if it's a 50-50 fair coin, then 10 point whatever half of 07 is, 10.035, I guess, % of the time, I would guess 2 white, 3 black, and the other 10.035% of the time, I would guess 3 white, 2 black. So just split this percentage in half, that's what I mean. Okay, so half of this percentage. Okay, these are mutually exclusive outcomes, so we can just add up their probabilities. Let's just go ahead and do that. So 21.50 plus 25.08 plus, and then I'll just do 1/2 times 20.07%. And I want to actually see what this is because I think this is interesting. Okay, so this is what I'm getting. I just paused and used a calculator. 56.615%. Okay, so even with only shaking up the marble box 10 times, you already have a better than 50% chance that you actually guess the correct proportion of white and black marbles in there. This might seem like a really silly question or like really strange or something, but would you risk your life on this probability of being correct? Like if it was a life or death decision that you know what's in that box, would this be a high enough probability that you're right? I don't think so. It wouldn't be, right? If I had to risk my life, I'm not shaking up that box 10 times. I shake it up 1,000 times, 10,000 times, 100,000 times, right? And this probability of being correct would hopefully then be going up and up and up. This might seem like a kind of dumb discussion, but actually a lot of decisions in life are made based on statistical probabilities. Whether to use this medicine or that medicine, this treatment or that treatment, whether we should build a road in a certain place, whether we should allow people to go a certain speed on the highways. These things are based on statistics, and they are life and death decisions. So probability that you guess wrong, well, this is your probability of being right, so it's just 1 minus that. Or 100%, since we're in percentage form here. So whatever that turns out to be. Okay, I will see you guys in class.